Hello everyone, and welcome back to NL 582, Modeling and Control of Electric Machines and Drives. So last lecture we finished talking about the recap on AC circuits and three-phase systems, and we started talking about the basic principles of rotating machines. So the course is all built around rotating machines. We're trying to model them, study their construction, theory of operation, how they work, how to mathematically model them, how to predict their performance, and how to control them, that we call the electric drives. Okay, so before jumping into details of the different types of machines and how to use them, or what is the differences between them, we need to build a foundation about basic principles that applies to almost any kind of electric machines. So we started talking that the electric machine is basically an energy converter, and it has two types, main types, which are the motor and the generators. The motors take electric energy and convert it in the presence of a magnetic field into mechanical energy, that means rotation. And the generator takes mechanical energy from external source, something that can rotate its rotor, its shaft and rotor, inside a magnetic field, which is also your medium of conversion, and this will convert this into electrical energy. That means an electric voltage will appear at the terminals of the coils of this generator, and then if you apply these terminals into an external load, an electric current will move out of the generator to the external load. Okay, so you have those two types, the motors and the generator, and they are basically the types that we're more concerned with. We talked about that the transformer is also considered a machine because it's also an energy converter, but it's not have a mechanical part, it does not rotate, so that's out of our scope for here. Okay, the other thing that we talked about, that any kind of machine that you will be focusing on, and that is the most common shape of electric machines you can face in any industrial facility you'll be facing, that will be have two members: the stationary member that does not rotate, which is the stator, and in the typical case that will be in the outer frame. So this is your stator, like here, the outer cylinder, and your rotor will be the inner cylinder, and this rotor should rotate around its axis, and this axis is the shaft, and the shaft, this can be connected to any other mechanical system outside this. If this is a motor, then this shaft will transfer mechanical energy that has been developed inside the motor to the outer, and then you can attach to this shaft anything you want to rotate with this. Whether it's a fan, a pump, any kind of production line you want to drive, if it is a car, if you're talking about an electric car, and all about that. If it is a generator, the shaft is the thing that you attach a turbine to it, and a turbine is something like a big fan with blades, and then you use external source to rotate this turbine and then rotate the shaft, and this rotates your rotor inside the machine, and this in the presence of magnetic field will have the backward energy conversion, and now you have a generator to generate electricity from it. So you have a stator, a stationary member, and a rotor, a rotating member, and between them there has to be some air gap, some gap between them to allow the rotor of the machine to rotate freely inside the stator. We said that we're trying to reduce it as much as we can, but we cannot cancel it at all, otherwise we will not have any rotation. Okay. The third thing we talked about is actually the magnetic field, because it's our medium of conversion. We said we need to have a magnetic field inside our machine, and the sources of magnetic field are basically two sources: a permanent magnet and an electromagnet. An electromagnet is basically a coil that is fed from an electrical source, because it has been found that by experiments is just if you have a wire, any piece of wire, if it is just a wire, or you wrap it to make it a coil and attach it to an external source so that there is an electric current moving into this coil, there be a magnetic field will be generated from this coil. So it's now being converted into a magnet. Yeah, it's called electromagnet. We talked about the differences between them. The very main obvious one, the electromagnet is basically controllable. You can control the magnitude and the direction, which means the polarity, so you can control the magnitude of the magnetic field we're getting out of it by controlling the magnitude of the current moving. And you can control the polarity by also controlling the direction of the current moving. If you switch, or you just inverse the direction of the current moving, you will be reversing the polarity of the magnets. That means the North Pole will be a South Pole and the South Pole will be a North Pole. That is something we cannot do with the permanent magnets, okay? So, going more with this, we now said that our more flexible friend will be this coil with the electric current moving through it. So, we talk a little bit here about wires. So we talked that if you just got a wire and you have an electric current moving through it, so if it's just a piece of wire like this, and you find here some electric current moving through it, you will be basically having a magnetic field generated around it like in cycles like this. Okay, so this guy we call a wire. Sometimes we call it just a conductor. Okay, but this is not the most effective way we can find, just because just a single piece of wire, it will not make you a very good shape, concentrated shape of magnetic field. So most of the time we do not use just a single wire like that. Rather we use a turn. So we take this piece of wire and just have it on this shape. So this is the turn. So we just make it like this. Okay, I just turned around to make it a turn. So this guy is just turn. Okay, let me, yeah, okay. So this is considered actually just two wires, because you will have different wires here. So this is a wire, and this is a wire, and this is a wire. Actually, they're all just one wire we turned around to make it a turn. But in theory, you'll just look at it as just three wires like this. Okay, so this is a wire or a conductor, and this is a wire or a conductor, and this also can be a wire, but we call it the overhang, or sometimes we call it the end winding. Why are we saying this? Because this part does not contribute in the energy conversion process, and we will know why in just a minute. Okay, but even just one single turn like this will not do the job for us. So most of the time we have a bigger than that, not just one single turn like this, but we turn it to be more. So we have more turns. So I will have a turn like this, and then I will go to have another turn like this, and another turn, and the more you can have to get whatever number of turns you have. Okay, so these multiple turns, now we call it a coil, and that is the thing we'll be using all the time. Not just one piece of wire, not a single turn of wire, but we will having multiple turns to get a coil. Okay, and that is the more concentrated shape. You can see it like this. Okay, and if it is a coil like that, we will call this a coil side, and this also will be a coil side, and this is still called the same, the overhang or the end winding. Okay, and those 2 points is your coil terminals. Okay, so that's what we'll be doing was all the time. So I'll be talking about a turn that consists of 2 wires. We're talking about a coil that have 2 coil sides. Each one of them will have some amount of wires into it. Okay, so that's just basic idea. We have these wires or conductors connected to have something like this. Okay, so going from just a single wire or conductor, you can turn it to make it one turn, and you have multiple turns, and now you have a coil. Okay, so the coil is some turns, and the turn is just 2 conductors. If you can go further with this, so more than one coil connected together in series or in parallel is called a winding. Okay, so you can have just not one coil like that, you have 2, 3, 4, whatever you want, and you just connect them together in series or in parallel, and now you have a winding. Once they are connected together, they are together called a winding. So the winding is some coils, and the coil is some turns, and the turns is 2 conductors. Okay, so that is the idea. It's just their terminology to have in your mind, because it will make things easier with us while we going on in the course. Okay, guys? So knowing this, we can now, these terminologies and these basic principles, we can now turn around to try and have a look at a simple machine. So let's build a very small simple machine and say how actually machines work, and what about those machines, can they work, or what is the basic construction of this kind of machines. So let me grab a photo here. So just trying to be as realistic as I can, and this photo is taken from a YouTube video that's from a website called learningengineering.com. So you can actually search for this video, it's a very good one, but we will just go step by step here. Okay, so that is a very simple shape you can find of a machine. Okay, that is, you have a magnet like this, so there is a north pole, okay, and a south pole. That means you have flux, magnetic flux like this from here. So you have magnetic flux, and we talked about that our magnetic flux, by the way, can be magnetic flux or magnetic field. They are the same. Okay, so a magnetic field going from the north pole to the south pole. Okay, so this can be a permanent magnet like this, or you can just simply make it an electromagnet by just having a coil like this here around this, and this coil is just having here an electric source, and you have current moving through here. So, and it'll be the same idea on the other one. Okay, so this can be, those north and south pole can be a permanent magnet or an electromagnet, whatever it is. Okay, so just we need a source of magnetic field like we said before. Okay, and you need to have at least a coil like this. Okay, so like the coil you're seeing inside here, so this guy is a coil, it's multiple turns like this, and here's your coil terminals. Okay, and this coil is just placed inside the magnetic field, so the magnetic flux lines cuts this guy. Okay, guys, and in something like that, we have the outer north and south pole like this is your stator, actually. So that is the stator, those magnetic poles like this, and your rotor will be something like this. So it's omitted from here to make it more clear, but you will have some sort of a cylinder inside here, and this coil is just wrapped around this cylinder, and in the middle of this cylinder you will have the shaft, the axis that the machine will start rotating around. Okay, so this guy is the thing we will have rotation like this. Okay, and that is your coil. Okay, so to have some sort of electric machine, you will all the time need to have those two members. Okay, so you need, so to build any kind of machine, we need a coils and magnetic field source. Okay, so those you need to have. a coils that will have electricity into it and a magnetic field that will have the energy conversion process happens. Okay, guys? And now you can have rotation. If you apply rotation from an external source, you are having a generator. Okay, so if we apply external force to rotate the coil inside the magnetic field. What I mean by inside the magnetic field, cutting the flux lines. Okay, then you will have, we get electric voltage induced on the coil. Okay, and that is a generator. Okay, so that is simple as this. If you want to have a generator, if you want to generate electricity, you just get north and south pole like this. That will give you a magnetic field, and have a coil placed inside this magnetic field, and you rotate it, and now it cuts this magnetic field. Okay, and now you have a simple generator, like we said before. Okay, guys? So I'm gonna just go with this for further like that. When we get this, we get this from Faraday's law. Okay, so Faraday had this experiment about this. He got just a simple coil and have it and started moving it inside a magnetic field to cut it, and he just figured out by measurement just there is an electric voltage induced at the terminals of this coil. Okay, guys, and that's why he get his generator principle. And now we are having the same thing doing around. We're having just the north pole and south pole. This will give you magnetic flux lines, and if you place a coil inside them and start rotating this coil, so now you have this rotation or movement inside the magnetic field, and electric voltage will be induced at the terminals of this coil, and now you have electric voltage out. That means you have electricity. So you need to have magnetic field inside and then apply mechanical force from out. That's external mechanical force. Okay, and now this mechanical force applied from outside, it will be converted into electrical energy by the voltage that appears at the terminal of the coil. And that's what we mean by energy conversion. That's what we mean by a machine. Yeah, that's very, very simple shape of machine, and we will be trying to enhance this shape as much as we can, to enhance its quality as much as we can. But that is the basic principle here, guys. Okay, so looking at this kind of machine, if I just try to look from here an elevation like this, just to make it more simple for you to see, it will be something like that. Okay, sorry. So that is will be your south pole, and this will be your north pole, and inside them will be the rotor cylinder we'll be talking about, and the coil is just wrapped around it like this. So those are two coil sides. Okay, it is the same like this, guys, but I'm locking from here like this. Okay, so if you lock from here this direction, you will just see the coil as 2 points from here. Okay, and this is your axis of rotation, and it is rotates like that by a speed omega. Okay, so omega is the speed of rotation, okay, in radians per second. Okay, so the speed of rotation can be like this in omega, which is the angular velocity, or can be any type of other velocities. We'll be talking about them, but it's just a speed. So you're talking this rotor rotates around its axis by some sort or some value of a speed. Okay, and now this cuts the magnetic flux lines coming from this guy, so the North Pole will just project magnetic flux like this, going from the North Pole to the South Pole. Okay, guys? And yeah, so you will have flux lines like this. Okay, something like this. And now these flux lines cuts your coil, which is the red and blue dots, those are your coil sides. Okay, guys? But why I'm just not plotting those flux lines and they are all straight like this? Why I'm just having these shapes? Okay, that is a principle you had before when you talked about electromagnetic fields in the past. Okay, that is the magnetic flux lines tend to cross through materials with higher magnetic permeability. Sorry, excuse my writing. Okay, just like an electric current tends to move through materials with higher electric conductivity. Okay, so if you remember, if you're talking about an electric current and you try to move it, we make our wires from copper most of the time, and sometimes also from aluminum. Why? Okay, so the high electric conductivity you're talking about here mostly will be copper or aluminum. Why? Because they have higher electric conductivity. They are materials that will face the electric current with very low resistance. So the current will face low resistance in them, so he likes to move through them rather than other materials like wood or paper or something like this. Okay, the same idea with the magnetic flux lines. The magnetic flux lines likes to move through materials that we call magnetic materials. That means they have higher magnetic permeability. Okay, so the same principle, that the magnetic flux lines will face very small resistance to their movement inside into it. Okay, guys, so this needs high magnetic permeabilities. So we make our machines cores, we make our holders. So that we said before, that we have a cylinder here, this cylinder, to hold our coils. Okay, why we have a cylinder like that? Why we just leave the coil into the air like this in this photo? Okay, yeah, we can do this, but if we have a cylinder like this from a material that have high magnetic permeability, and materials that have high magnetic permeabilities like iron and steel, so those are the materials all the time we are building our machines of them, because they have high magnetic permeability, so the magnetic flux lines will tend to move more through them rather than moving through the air. Okay, so this will give you a uniform shape of flux lines, just like you see here. If you don't have this cylinder like this here inside, which made of iron or steel, you will not have just a uniform shape magnetic field like this. And the more uniform shape magnetic field like this, you can direct the field to the spot you want inside the machine. And we are directing it into the coil, because the more magnetic field cutting this coil, the more energy conversion that happens. So we need to do this. Okay, yeah, it's not very good, because the more iron and steel you put, that means the more heavy your machine will get, and this will need more installation requirements. That means if you want to transport it from a manufacturing facility to the customer, or you're trying to raise it to very high altitudes, like if you talk about a wind turbine or something, the wind turbine are very high in latitude. So if you're trying to have your machine, which is the generator, which will be installed in this wind turbine, to this very high level of latitude, when it's heavy like this, because we are just building it from iron or steel, it will need more power and. Okay, but again, we cannot avoid this, because these kind of materials is the materials that the magnetic field likes to cross more, and that is the way we can direct the magnetic field to the zone we need. Okay, so rather than just placing your coil in the air like this, you place it around an iron or a steel cylinder, and now the magnetic field will come directly to it, because he likes to move through this steel or iron. Okay, guys, so that is the idea we'll be talking about. Remember when I talked that this air gap here, so that is your air gap. Okay, so this here and there is your air gap. Sorry. Yeah, we said we will try to minimize as much as we can, but we cannot cancel it. We cannot cancel it, because if it is cancelled, the rotor will not be able to rotate at all. Okay, so we need to have some gap, but we try to reduce as much as we can. I didn't tell you why we try. Now I'm telling you, we reduce it as much as we can, because again, the magnetic field tries or likes more to move into iron rather than into air. Okay, the air is not a magnetic material. It does not have high magnetic permeability. Okay, so the magnetic permeability of the iron or steel will be in terms of 1,000 times than the air. Okay, that means the magnetic field will face very much higher resistance in the air than it's compared in here inside the steel of this or this. Okay, so this North Pole and South Pole are from magnetic materials. The flux lines tends to move through them, and the rotor here is the cylinder made from iron or steel, and again the magnetic field likes to move through them. But the air gap inside, that's air, and it have very high resistivity for this magnetic fields to move into it. We call it reluctance. So this have very high reluctance. So the reluctance in magnetic field, the reluctance is just as the magnetic copy of resistance. Remember the resistance, electricity? The same principle we call it in magnetism is the reluctance. So the air has very high reluctance to the magnetic field compared to the iron or steel. Okay, so we need to minimize this air gap as much as we can to minimize this resistance, the reluctance for the magnetic field to pass. And again, because our magnetic field is the medium of conversion, so the more magnetic field we have and the more consistent shape it has, the better energy conversion that will happen inside our machine. Okay, guys, and that's why we are building our machines mostly from iron or steel pieces. Yeah, they are expensive relatively, and yeah, they are heavy, but they are the best mate for the flux lines, and we need to provide our flux lines with the best environment ever, because that's our medium for energy conversion. Okay, guys, so that is the very simple shape of a generator like we said here. Okay, so to have a generator, from this machine, simply do this. Use external source to rotate the rotor, which carries a coil, cutting the flux lines of the magnetic field coming from stator, okay, and then electric voltage is induced on the coil that can be measured on the coil terminals. Okay, guys, that is Faraday's law for generation, and that is simply how you build a very simple generator like this. And it's the same principle applied to the very big giant generators you will see on power plants. It is the same principle. The whole point is how to do the engineering of this. How to build the stator in a very good shape, and how to build the rotor in a very good shape, and how to build or find the coils and where to place them. It's just the idea of the design of this to maximize the energy conversion to the very high point, okay? But the principle holds the same. It is this very simple principle, okay? If you don't write the math of this, so that is the equation from Faraday. So the electric voltage that can be induced is just E equals V cross B dot L. Okay, guys? So what is this? So E is the electric voltage induced, okay, in a wire. So this equation holds to just a piece of wire in volts, okay? And when I say induced, just to make it clear for your mind that we're talking here about induced voltage, not a voltage you apply from a battery or something. That's voltage that get be induced, generated, okay? So it is electric voltage induced, or you can call it generated, okay? So this V here is not voltage. Don't get confused here. So the V is the linear velocity in meter per second. So we talk that we have to rotate our rotor inside the magnetic field, and this rotation now is measured in linear velocity meter per second, okay? And now this B is the magnetic flux density in Tesla, okay? So that's how we measure the magnetic flux density. A magnetic flux density is basically the magnetic flux divided by the cross-sectional area of the material he is just moving through, and that's the idea. L is the conductor length in meters, okay, guys? So from this equation you can figure out the same idea of how to get electric voltage induced, how to get electricity generation. This equation tells you this: if you have a wire of length L moving with velocity V inside E, or let's say it not inside, way better, cutting a magnetic field with density B, a voltage E will be induced, or call it generated, across the wire. Okay, guys? So that is how to calculate this. Okay, how to calculate the amount of voltage that will be induced or generated across this conductor. Okay, like here is just cross product and dot product because they are all vectors. Okay, guys, the V, the velocity, is a vector, and the flux density B is a vector, and L, the conductor length, is a vector. So to do this, you need the cross product V cross B, and then the result of them, which will be also a vector, will be dot product with L, with the conductor length. This will give you E, the induced voltage E. Okay, guys? And I hope you remember this vector calculus, vector calculation like this, to find the V cross B. Okay, it will give you, or you can calculate it like just the magnitude of V multiplied by the magnitude of B times sine theta, and theta is the angle between the two vectors V and B. That is just the magnitude of it. Okay, so that's how to find the magnitude. To find its direction using the right hand rule. Okay, just as a refresher memory, you should be knowing this very well, but I will just grab you this photo. Okay, very big. Anyway, so it'll be something like this. Okay, it will be just saying those, you will have your three fingers of your right hand, the thumb, the index, and the middle finger. So the thumb goes, they are all perpendicular to each other, like you see in this photo. Okay, and you just, the thumb goes with the first vector, which will be here the V, the velocity vector. So this will be V, and the index finger will be going with the second vector, which will be the B. And then you can find the direction for the cross product like this cross product, and you can find the V cross B direction in the middle finger direction. Okay, so you can find its magnitude from VB sine theta. And for here, actually, V, B, and L, the three vectors here, are all perpendicular. That means you'll have a 90 degrees theta between all of them. So sine theta here will be sine 90 equals 1 all the time. So don't bother about this sine theta stuff because they are all perpendicular to each other. So V cross B, this cross product will be just V magnitude multiplied by B magnitude, and its direction comes from this cross product right hand rule like this. You place your thumb in the direction of the velocity of the movement of the rotation V, and your index thumb into index finger, into the direction of the magnetic field, and then your middle finger will point to the direction of this cross product. Okay, why we are doing all of this? Because we need to quantify the electric voltage that we'll be having from our machine. Okay, so I'll be turning you back to the image we had before, and let's quantify this, okay? Using this rule from Faraday, V cross B dot L. Okay, so I'll get the same photo again. Okay, guys, and now let's quantify it. So, like we said here, we will have in this coil, we have a conductor like this here, and another conductor here, and a third conductor like this here, okay? I'm gonna call this terminal point 1, okay? And I will make it red in color like this conductor. And the other conductor will make it blue like this, and this will be calling this terminal point 2. And I will leave the other one and call it 3 like this, green. Okay, guys? And let's figure out, because this equation will give you the induced voltage in just a single wire. Okay, so we will calculate the induced voltage in this turn like this. If you just one turn like this, we calculate the induced voltage in it in a wire by wire. So just go to this first wire, the red wire, and then the green wire and the blue wire, and find the induced voltage in each one of this. And because they are connected all together, we can just sum the voltages of them, and it will give us the total voltage induced in this turn, like what you can see here. Okay, guys? So how to do this? Simply like this. If you want to find the E, it will be V cross B, and once you get their value, you just dot it by the L, which is the length of the conductor, like this. Okay, guys? So if you're starting here from 1, this red one, so the conductor goes in like this, goes like this, and come back. This gives you the direction of L, the length of the conductor. And then let's, for example, say that we will have this rotated like this, anti-clockwise. So this is the omega, the speed of rotation, but that is not the V. The V is just the linear velocity, so it comes linearly. We'll be saying this, okay? So that is the point we'll be having here, one by one. Okay, guys? So if I try to look first at conductor 1, the red one here, okay? So if this rotated like this, anti-clockwise, that means the velocity on this guy will be just wording towards up like this. So this is V. Okay, because this will rotate up like this, because like this it will rotate anti-clockwise. Okay, guys? And where is the magnetic flux density? You have here the North Pole and here the South Pole. That means your flux density comes like this. So the flux density direction will be constant all the time from left to right like this. Okay? So if you apply your right hand rule for the thumb, so you have the thumb pointing into V and the index pointing to B, your middle finger will be pointing to the direction of their cross product, and this will be the direction also of E. So this will be just going inside the paper like this. So this will be the direction of E1. From your circuits, this direction means you have a negative voltage sign here and a positive voltage sign here. Okay, guys? And this cross product will be lie in the same direction of L, yeah? So L will be just going with the conductor itself. So that is the direction of L, okay? Which is the same direction of the conductor itself, going into the page. From 1 inside the page, okay? And this is also the same direction of the cross product you just have, V cross B, from your right hand rule, okay? That means after you get VB, okay, its angle with L, because you'll need to make another dot product here, will be angle 0, and the dot product, if you remember, is just the magnitude of the first vector multiplied by the magnitude of the second vector cosine the angle between them. Now you have angle 0, cosine 0 is just equals 1. And that's why we told you they are all perpendicular to each other, though we don't need at all to just bother around the angles. Okay? So the voltage here will be negative at 0.1 and positive inside, and now you have E1. Okay, guys? I'll be doing the same one with 2. Okay? It will be the same idea. But now V will be pointing down like this. Okay? Because it's just rotating anti-clockwise. Yeah? And B still in the direction here. Yeah? If you apply ortho the right hand rule again, it will give you the direction of the induced voltage coming out like this. So that is E2. That means you have a negative inside here and a positive outside there. Okay, guys? So this can be quantified. So E1 before moving around will be just VBL. Okay? And just without the dash vector, that means they are all the magnitude. So that's the magnitude of V multiplied by magnitude of B, magnified by magnitude multiplied by the magnitude of L. Okay, guys? And if you want to find E on conductor 2, which is the blue one, okay? Also, by the same idea, V cross B dot L will also equals VBL, because they are all also perpendicular, but with the direction like you see it here, from inside to outside. The negative is inside and the positive is outside. That is the blue conductor E. Okay? But what about the third one? 3. Okay, guys? The point here is in conductor 3, the direction of the cross product V cross B will be perpendicular to L. Okay? Why? Because this L, that is the direction of it. It's perpendicular to both the direction of the red and the blue ones for 1 and 2 conductors. Okay? So the V and cross B will give you something perpendicular to it. It will be something like that. So if this is 3 like this, you will having the flux density just going, the V cross B will be something like this. And here's the L. Okay? Make sure that is L, not E. Okay? So they are perpendicular to each other. That means this dot product here will be cosine angle 90. So cosine 90 is 0. So E3 equals 0. So there is no induced voltage in this conductor. And that's why if you go back here, when we just start talking about in-3 thing here, when I've told you about the conductor coils, remember, we called this part of the coil, this part of the turn, the overhang or the end winding. We didn't consider them just a wire like those guys, because there is no induced voltage in them. They are not contributing in the energy conversion process. Why? Because of its position like this. It will be just in the same direction, just here, in the same direction of the flux lines. So the flux lines goes like this, and this is just parallel to them. So, like we said here, the induced voltage by the calculation, if you try to calculate it like this, it will be just E equals 0. So there is no induced voltage in it, and we don't need it. Okay, so if you can get rid of it, just go and get rid of it, but actually we cannot, because we need to connect the two conductors 1 and 2 together, and we don't have any other means by connect them by this piece of wire, which most of the time does not have any induced voltage in it. So that's why we call it the overhang or the end winding, because just something we use to end our winding, to connect our two pieces of conductors 1 and 2 together. Okay, so if you want from here to find the total E of the total turn, because it's just one turn, from your scene here, it will be E1 plus E2 that will be 2 VBL. Okay, guys? And now the complete turn like this here, and so this is terminal 1 and that is terminal 2. Okay, and like we said, E1 will be like this, so that is negative and that is positive, and E2 will be like this, so that is negative and that is positive. So the total turn, the total induced voltage you will find here, the E of the turn will be 2 VBL with these terminals, that is negative and that is positive. Okay, guys, that means your small generator like this will be if you apply an external load to these terminals, like a resistance or something here, you will have an electric current moving from this positive terminal and coming back going to the negative terminal like this. And that's how you build a small generator and even quantify the amount of voltage that will you get out of it. Remember, that's just E of one turn. If you have multiple turns, which is the typical case, you just multiply this by the number of turns. Okay? You just have copies of the same turn like this, goes over and over and over, so they will all have the same amount of voltage, 2 VBL. So you can just multiply this by the number of turns you have inside your coil, and you have the voltage induced in the entire coil. Okay, guys? So that is the basic principle of how to build a small generator, how to get electricity by just rotating the coil of it inside the magnetic field, and how to quantify this amount of voltage you get and how to find its magnitude and its direction. Next time we'll be continue working through this, and we'll be talking about how to build a small motor. Actually, it will be the same construction like this, but rather than getting voltage out of it, we'll be applying external voltage to it. I will be see what will happen, how this machine, small machine, can rotate, and will be the same principle that you'll be applied to any kind of a motor you'll be studying after this. Okay, so yeah, thanks so much for joining me today. I have some time to study this because it'll need study to just fix in your mind, and I'll be happy to answer any questions you have on Friday morning's meeting that we have posted the information about in our D12 page. Thank you so much for joining me today, and I'll be seeing you next time.